Hello everybody, welcome to Introduction to PyTorch for Beginners. My name is Dawood Wadi and I'll be talking about PyTorch, and then we'll go to the code and see how PyTorch works. You're expected to have a beginner's understanding of Python, specifically NumPy. In addition to that, a little bit of data science knowledge will be required. So PyTorch is a deep learning framework created by Meta, formerly Facebook, and is a huge contender in the realm of deep learning frameworks. If you talk about the popularity of PyTorch, specifically in the domain of AI research, you can see the top 20 publications based on paperswithcode.com. And as you can see in the top 20, around 5 of those were built with TensorFlow, which is one of the biggest rivals for PyTorch. And 7 of them is made by PyTorch. So that's kind of historically speaking. The top 20 trending publications on Papers with Code, which are basically papers that have been recently published. The majority of them, around 12, have been published in PyTorch, and only a couple of them have used TensorFlow. So not only it's a dominant deep learning framework for state-of-the-art AI research, but also it's gaining more and more popularity, and it's kind of creating a monopoly in terms of the deep learning frameworks. So many of you might have already learned TensorFlow, and you might want to consider switching to PyTorch. Here's another chart showing the dominance of PyTorch in the repository creation starting from September 2019, where there was kind of a competition between PyTorch and TensorFlow. Still, PyTorch was more dominant. But as the time passed, with the advent of Stable Diffusion released for PyTorch, large language models in open source format like Llama 2, you could say the majority of AI research is using PyTorch. So what does it mean? It means if a new model comes out, shows some state-of-the-art performance, you'll inevitably have to learn PyTorch to be able to use them. It doesn't mean that these new models would not be made for TensorFlow. It depends on the community, specifically TensorFlow community, to go there and actually kind of write the new model for TensorFlow. But that could take a while, basically. To do a side-by-side comparison, PyTorch is one of the most Pythonic frameworks. So whatever you do in Python, the syntax is pretty similar, specifically similar to NumPy. It's pretty easy to debug, so you can change different variables and see their outputs. On the other hand, TensorFlow has a high level of boilerplate. That's why most people know TensorFlow through a higher level API like Keras. Probably the most important distinguishing factor for PyTorch is the dynamic computation graph for fast experimentation. It means you don't really have to compile everything before you can see the results, the inputs, the outputs of the model. On the other hand, if you work with TensorFlow, you've probably seen, because it has static computation graph, you need to compile it first. So it's really hard to do research or experimentation using TensorFlow. In terms of high-level APIs, PyTorch has a couple. One of them is PyTorch Lightning, which tries to replicate what Keras did for TensorFlow, training models, defining model architectures easier, and also Fast AI, which has abstracted away a lot of boilerplate in PyTorch. And a similar high-level API for TensorFlow would be Keras. So This session is supposed to be hands-on, so let's go into Jupyter Notebook. If you're just starting out, you might want to pip install PyTorch. So let us try doing that here. Okay, so I'm running Jupyter Lab locally. You might want to use either Google Colab or Jupyter Notebook locally. So pip install torch. It will install the basic version of PyTorch. If you're looking for GPU support, you need to put a specific code here. So one way is to go to pytorch.org, click on get started. And then here, select the version, your operating system, whether you want pip or conda, Python, and depending on the hardware you're running, you would need to choose CUDA or ROCm for AMD GPUs or the CPU version. So pip install torch will install the CPU version, but for CUDA, you need some extra lines. Okay, so after we've done it, we're ready to experiment with PyTorch. I would say first we should have a look at comparisons between PyTorch. So let's import Torch, which is PyTorch, and import NumPy, NumPy as in P. Okay, so my claim right now is PyTorch's syntax is pretty similar to NumPy. Let's test a couple of things out. So you usually say, I want a NumPy array, so let's call it array. It's an NP array, and you can specify the elements of this array, which is n-dimensional. Let's say 1, 2, 3, 4, 5, 6. And if you show this, you basically will see, let me double check. Yep, I forgot square brackets here. You can see you have a 2 by 3 NumPy array. And if you want to replicate the same thing, in PyTorch it's called a tensor, so you can call it tensor, torch.tensor 1, 2, 3, 4, 5, 6. And let's have a look at our tensor. So it's pretty similar in terms of how to create tensors and the output. The tensor, just like a NumPy array, has this shape attribute, so it says it's a 2 by 3 tensor. The kind of mathematical difference between tensors and arrays and matrices are beyond the scope of our conversations, but we can treat them kind of identically for now. Okay, so let's say I want to reshape my tensor. So basically you can call reshape on the tensor and say I want all the elements in one dimensional vector. Or I can swap the axes and say 3 and 2. It will kind of transpose it. Same thing with NumPy. We can index into elements of a tensor. So we can say tensor. First, let's have a reminder of how the tensor looks like. 1, 2, 3, 4, 5, 6. So I can say tensor and I say first element or first row and second column. It should return 2, and it does. You can select the whole row, all of the rows, and the first column or column index 1, it should give you this column. So indexing into PyTorch's tensor is similar to NumPy arrays. And we can do basic operations. If I have a tensor number 2, so tensor 2, let me copy paste this and say my tensor 2 would be negative. So -1, -2, -3, something like this. So this is how my second tensor looks like. I can multiply them. So I can say tensor times tensor 2. And it's what it does, element-wise multiplication between the two tensors. You can sum them up. So basically tensor plus tensor 2, and it was element-wise addition. Well, in this case, the first row will cancel out. It has the statistical operations like mean, so I can call mean on it, similar to NumPy. It says mean could not infer output D-type. It must be a float or complex D-type. So it takes issue with the fact that our tensor right now is an integer. In these cases, since PyTorch has to automatically do differentiation in the AutoGrad, it does these checks as well. So I can just cast it to a float by calling float here and then take the mean. So just calling float will turn everything into float, and then I can take the mean. Okay. Now, we see most of the functionalities in NumPy are shared with TensorFlow as well. I'm sorry, with PyTorch as well. Another thing to note now is, why do we use PyTorch? What's the added benefit that PyTorch gives us that NumPy doesn't? And that's automatic differentiation. If you've looked at neural networks before, you already know differentiation and calculating gradients is the backbone of neural networks because they use an algorithm called gradient descent. So, how can we activate the AutoGrad in PyTorch? How can we ask PyTorch to keep track of the gradients? If I go back and create my tensor now, so I'll just copy paste the code. And in addition to the numbers in my tensor, I would say requires underscore grad equals true. Then if I print it out, of course it has to be float. So let me put some dots here. Then it shows a flag called requires grad equals true. Now, any operation I do to this tensor, PyTorch will keep track of it. So if I create a new variable called the summation, and that would be basically my original tensor, all the elements summed all over. And if I display it, it tells me the summation of the elements is 21, and it also shows me a grad function. So it says the gradient function is summation backward. What does it mean? So now if on my summation variable I call backward, I'll basically ask PyTorch to do a backward pass or create the gradient of a summation with respect to all of the elements in my original tensor. All right, so let's see how this looks like. There's no output because now each element in the tensor will contain gradients. How can we access those gradients? So if I call a grad on the tensor, I can see the gradients. Let's put them side by side. So the actual tensor up top, this is the actual tensor, this is the gradient. The gradient, again, is the partial derivative of summation with respect to each of the elements. When you sum up a bunch of variables, well, their gradients with respect to the summation would be 1. Because if you change each one of these variables by 1, the summation will change by 1. Let's look at another example. So let me delete some of these. So let's delete summation. And using my tensor, let's create a second variable called sum2. And to create sum2, I will multiply tensor by 2. That's where the 2 comes from. And I'll get the result and take the summation now. So before I take the sum, I just multiply by 2. So now my sum2 has a value 42. So if I call backward on sum2, it should now calculate the gradient of sum2 with respect to my tensor. What happens here? What happened here is the new gradient is added to the previous one. So the gradient of sum2 with respect to tensor, since it's multiplied by 2, would be 2. Now I call backward twice, once here for sum2 and the other time on the summation. For this summation, the gradient was 1 for each element. For this sum2, the gradient is 2, so it added them up. So you don't really have to trace back and see why the gradient is 3 or 2 or 1. You just have to know at the end of your operations, you have to reduce your values to a single element tensor, call backward on it, and then it will calculate the gradient of your inputs and parameters for that particular operation. And then you can use gradient descent on it. So that's the first part. Now, how can we use PyTorch to solve a real world problem? It might be a bit too soon for real world problems. So before that, let's solve a relatively straightforward problem. I'm going to generate some points. So I'm going to say my x is a bunch of random normal numbers. Similar to NumPy, we can create random normal numbers. Specifically, I want 100 of them, and I want them to be one-dimensional. So let's have a look. This is my x. Then that's going to be my input. Then I will create a y variable, which is x times 4. So it's a really simple line. Now I would add a bit of noise to it. I would say to my y equals 4x line, add some random noise. We have 100 of x's. For each x, add some noise. And it should give me my y. Here we go. Then I can use matplotlib. So import matplotlib.pyplot as plt. And I would just simply ask for a scatter plot, x and y. So let's see what we have here. We have one of the most basic questions in data science where we have a y or output variable and an x input variable. And we want to model them using a simple line. So we want to find the best fit line that passes through these data points and has the minimum amount of mean squared error. So on average, every line should be closest to our best fit line. How do we find the best fit line? It mathematically has a closed form solution, so you can find the exact value for your line. Our task is basically, we want to basically say y equals some parameter w times x. And we want to find this parameter w, or the slope. We don't have any intercept because we want to keep it simple. Now, we can use gradient descent for this. To give an idea of how gradient descent works, let me create some potential w's that can work in our case. Since we generated our data, we can already cheat and know that the slope is 4. So we can generate some numbers in a given interval, let's say from 0 to 8. So some values bigger, some smaller, 50 of them. So these are potential w's. If you have a look, these will span from 0 to 8, equal spacing, 50 of them. Very good. Now the next step would be just to write a simple for loop and calculate the loss if we use each one of these w's. So if I, let's say, use w equal 1, what will be the loss? The loss basically will be mean squared error of y hat, which is w times x, and the true value of y. We didn't define mean squared error. PyTorch already has mean squared error for us, so I can import it from PyTorch. Say, the syntax might be a bit too long, but you can say from torch dot nn dot functional import MSE loss. So if I choose the slope 1, which is less than my actual data slope, I can calculate the mean square loss of the predictions and the actual value. So let's have a look at the loss. It says the loss is 10. If I choose 9, which is too large, loss would be 27. I want to get a sense of the loss surface. That's why I created these w's. So if I write a for loop and say for w in w's, every value of these w's, get the prediction, or y hat, which is w times x, calculate the loss, which is MSE loss of y hat and the true y, and I can add them to a list. So I have a list of losses, empty, then I can append to it loss. Okay, so I can get all the losses. Now if I plot this now for every w, what the loss would be, we'll see here a quadratic curve. That's because mean squared error is quadratic. But most importantly, lower values than the optimal will have a high loss. Bigger values than the optimal will have a high loss, and we have a global optimum at 0.4 where the loss is minimum. It's not exactly 0, that's because of the lack of capacity of our line to account for all the variations in the data. So even if we fit the best fit line, we still have some data points that don't fall on the line, but we can get the minimum amount of loss. So the intuition with gradient descent is if we calculate the partial derivative of the loss, the vertical axis, with respect to the horizontal axis, that gives us the slope. If we are on the left, if our W is 1 right here, the slope would be negative. So if we go towards the opposite direction of the slope, which is towards right or positive, we will get closer to the global minimum. On the other hand, if we are at 0.6, this is the slope or the gradient, it's positive, and we move towards the opposite direction of the gradient, our loss becomes smaller. So using this idea, gradient descent says, if you want to know the value, the optimal value of your W or the parameter, you can start out with a random variable, a random value for it. So I would say my W is a torch. Let's pick a random point here. Let's say 1. So it's a torch tensor. Now we want to keep track of the gradient here. So I would create a tensor, set it to value 1, and I call requires grad equals true. So now if I display my random weight, it requires grad. So whatever operation we do on it, it will keep track of those operations. Now, let's calculate the loss if we use this W. So the loss would be our MSE loss of the Y hat, or W times capital X, and the actual Y. Let's have a look at the loss. We saw it before, 10.84. Then the next step is to calculate the gradient of the loss or the vertical axis with respect to our W. So we do the loss backward, which we learned about recently. It will do exactly that. It will go backward, find all of these parameters, all of them that require grad, which is only W here. We didn't set require grad for X or Y. And it will calculate the partial derivative of the loss with respect to W. So now if I check W's grad, I'll see the amount of gradient. So this is negative 6.5. So if my W is here, 0.1, the slope would be negative 6.5. And if I go the opposite direction towards the positive, I'll come closer to the optimal value 4. So that's the intuition behind gradient descent. Now let's actually take a gradient descent step. In gradient descent step, we would say W at time t, or the new W, is the previous W minus the gradient. Well, we already know the gradient, so let's fill in the blanks. Previous value is 1. Let's verify it. 1. So 1 minus W dot grad would be the new value of my W. Now you might already see the issue. Gradient is not on the same scale as the original parameter. So here, if we go 6.5 to the right, we'll jump from 1 to 7.5. So our loss will get worse. So the intuition behind learning rate is obvious here. We say, don't take large steps. Take a small fraction of the gradient as your step. So let's scale our step a little bit by some value that we can set here. Is called the learning rate. So this could be a really small value, like 10 to the power minus 3. Let me actually assign it to its own variable. called LR or learning rate. Now I can say my new value is the previous value minus the gradient scaled by learning rate. All right, let's look at the new W. It's 1.0065. So maybe our step was a bit too small. We can maybe increase it a bit and try again. But the intuition here is we got closer to the true value. Now, I made a mistake here. I made an operation on W, which causes Torch's AutoGrad to keep track of this operation as well. We need to remember the gradient descent step should be done outside of our optimization. In other words, when we update our parameter, we should not keep track of the gradient of this particular operation. Torch has a remedy for that. It's called torch.noGrad. It uses a context manager, and any operation that's done inside this context, the gradient will not be calculated. Okay, so let's put them all together and see if we can find the best value for W. So I'll create a loop and kind of clean things up a little bit. So we have our X, we have our Y. Let's look at their shapes. 100 data points, one dimensional. Y is 100 data points, one dimensional. Let's create our W now and use a for loop to optimize its value. So W again is the torch tensor, just one number, randomly initialize it to 1, requires grad should be true. We can have a look at it. Now I can write a for loop that optimizes the value of my W. So I can say for. Now we have to define how many steps or iterations we should do. Let's go back here. If we started with 1 and take small steps, it might take tens or hundreds of steps to arrive at the best value. So let's just say for I for iterations, or iter in range 100. So what were the steps? First, we need to calculate y hat if we used W. So what is the y hat, predicted y? That was basically W times X. What were our loss? It basically was the MSE loss of y hat and the actual y. What's the next step? We need to calculate the gradient of loss with respect to our W, called loss backward. Then we can take the optimization step, but this time we need to remember not to track the gradients. So let's call torch.noGrad. And the optimization step is basically W equals previous W minus W grad, the gradient times the learning rate. So let's just call this gradient descent step. Okay. We saw this artifact before when we called loss.backward multiple times. It accumulated the gradients in multiple steps. That's the default behavior of PyTorch. And because of that, after we run this operation, after we do our gradient descent step, we should set our gradient back to none or 0. So it prevents accumulating the gradients. And I want some logging to happen here. So if I say if iter, let's say it's divisible by 10, so every 10 steps, print some metrics here. So I'll use an F string and say, tell me what the loss is, and print the loss. And by the way, we can specify here, let's say I want 2 floating precisions, and also ask for the value of W. So I can get W dot item. I don't necessarily need the W dot item, but it gets rid of the kind of PyTorch names. And this one also with 2 floating point precision. So that's a complete stochastic gradient loop, which runs for 100 iterations or epochs, calculates the predicted value of Y, calculates the loss, does a backward pass and calculates the gradients. In this part, it calculates or performs the optimization step by subtracting the gradient from the actual value, sets the gradients to 0 or none, and then prints the loss and the updated W. Let's see. So right off the bat, we get a loss here. It says element 0 of 10, so doesn't require grad. And does not have a grad function. So let's see what the issue is. We have W, X, Y hat, loss. So let's debug. It's always beneficial and useful to have a look at these variables. So here, something we did got rid of the requires grad flag. So let me see what happened. Requires grad by default for W is true. If I get a Y hat, the required grad for Y hat would be hopefully true, yes. So it's not here. Is it happening in the MSE loss? After the MSE loss, it still has required grad. And loss backward. Let's calculate the loss. Should have the gradient function, and loss backward should be operating. Okay, so it probably is happening after the first epoch. So let me just print the iteration each time and see where this issue happens. Okay, so let's get rid of some of these chunks of code. Set the W. Run it again. So the first iteration is running. We're getting the Y underscore hat, the loss, and the backward. Okay, that's kind of tricky. Let's see. So that's happening the first iteration. Okay, let me double check. Again, what the Y hat is. Y hat is correct. What the loss is correct. And backward is functioning properly. But in this particular while loop or for loop, we see error. Print iter. And by the way, I shouldn't use iter as a variable name because it's a reserved Python operation. It's a function. So let me just change it to I. Okay, so now it happens in the second iteration. Let's see what the issue is. Doesn't require grad and doesn't have a grad function. All right. There's some changes we can do for the time being. So I can say set the data of W as the data of the previous W in this loop. Let's see if it solves it. Okay, now it works. So here probably PyTorch took issue with the fact that we are reassigning a variable name, and by doing this, it set the requires grad flag to false. That's why we got the error in the second loop. Okay, so we did the first Python debugging now. Now imagine if for TensorFlow, you had to compile everything, and when you ran it, it was really hard to debug. As you saw right now live, how to debug in PyTorch. Okay, so let me look at the, let me get rid of this print and look at the loss. So loss starts with 10.80, which is the loss of W equal 1.01. It becomes smaller and smaller. We go 9, 8. And the W is keeping bigger and bigger. How can we make it faster? Well, we have different optimizers to try out instead of this optimization step that we just wrote from scratch. This is the basic SGD optimization. We can also increase the number of iterations, and let's print only every 100 epochs. So let's continue fitting this. Now the loss is going down. W is approaching the optimal value, which is 4. Okay, 2, 3. Let's see. Okay, 3.7. Now you might be wondering, the trick should be now, is the model going to basically, let me see, equals 0. I forgot this part. What happens when the model reaches the optimum? Is it going to jump over it? Here. If it goes down, the error gets closer to 4. Is it going to jump over and get into larger numbers, or is it going to stay here? Now, since the gradient becomes smaller and smaller, if it reaches 4, the gradient would be exactly 0. Therefore, it will stay there, ideally speaking. Let's see what happens here. So another 1,000 iterations, and you see we're getting close. Now we have a little loss. W is 3.99. So we're almost there. Let's optimize it a bit more. Now it bounced over the best value. So it got to 4, and then the values start increasing. Okay. How can we prevent that? So we can take the learning rate, which currently is 10 to the power of minus 3. Maybe we can decrease it a bit and say divided by 10. Run another 1,000 iterations, a bit more, a bit more. So it seems like it's staying there. Let's increase it a bit. Equals, let's say 5. All right, I want to know what the value of gradient is. So I will ask it to print AutoGrad and break afterwards. You see, the gradient is really, really small. It's 10 to the power of minus 4 times 9 negative. What we're doing here at this step, we're saying, take my wrong value, which is 4.03, which is off by almost 3%, and subtract from it the gradient, which is this little small value, times my learning rate, which is another small value. So our steps are basically 4.5 negative times 10 to the power minus 7. No wonder even after 100 iterations, the convergence is very slow. But that's a topic for another time. Optimizers, how to train an image recognition model, specifically MNIST using PyTorch. That's a topic for another day. And how to do kind of more advanced, state-of-the-art, recent ML tasks, how to create models. I'm going to discuss them later, but thank you so much for attending today. We basically introduced PyTorch. We showed how similar in syntax it is to NumPy. So if you already know NumPy, you don't really need to learn much. The only benefit that PyTorch has, or maybe the main benefit, is the automatic differentiation, where it can calculate gradients. And knowing that, we found the best fit line, specifically the value W, that would best fit this Y and X plot. We found it is somewhere around 4. Okay, so thank you so much.